In today's class, we'll discuss about the grid integration. Grid integration of inverters. So what is the meaning of this one? Right. So we need to integrate your inverter to the grid. Okay. So as and when, so you are integrating that to the grid, right? So you have to control, we have the ability to control the active power and the reactive power. Or you need to maintain the voltage across the DC side. So you might have three or four objectives. So one is the active power control, reactive power control, and the third one, so maintaining the voltage across the DC bus. And the fourth one is operating at unity power factor operation. Unity power factor operation. So these four are the some main control variables. So when we integrate into the grid. So here, so in previous one of our classes, when we discussed the active rectifiers in the last semester, so we have seen this, right? So how to control the inverter in current control mode or current control method and voltage control method. So in that case, in both cases, we maintain the VDC, voltage across the DC link, constant. So that means this is operating as a AC, the inverter is operating as a AC to DC, and we maintain VDC constant. So that is DC side voltage, or we regulated the DC side voltage, and as well as we maintain the unity power factor operation. So source currents are sinusoidal and they're free from reactive currents, or there, in other words, the reactive power is 0. And as well as, so along with that, so we also maintain the voltage across this DC side constant. So we discussed two methods. So one is the voltage controlled approach and the current controlled approach. And in that case, so we are not control the active power. So we are not control the active power, right? So now our objective is to control the active power, reactive power, so that is being injected to the grid. So first essential things, right? So when you are integrating to the grid, when you are integrating an inverter to the grid, so some of the things are essential, right? So one of the first thing is, so inverter, let us assume that we have voltage source inverter, right? So let us assume this is a voltage source inverter. So that means it is acting as a voltage source. Similarly, the grid, so grid is also a voltage source, right? So as soon as, so we are integrating to the, or as soon as we are integrating this inverter to the grid, right? So that means these two will operate parallel. So let us assume that this is grid. Okay. Okay. So now we are trying to integrate, so this inverter here. So that means we are operating, or we are bringing this inverter in parallel. So when two voltage sources can be parallel, so when it will happen? So when we connect two voltage sources in parallel. If you assume that, is it possible to connect two ideal sources parallel? If it is possible, so when we can do that? So when we can do that?
Same voltage.
Hmm?
When voltage is same.
When?
Voltage is same.
Voltages are same, right? So that means in case of DC and the voltages are same, in case of AC, if their instantaneous voltages are matching, so then only we can connect two AC sources in parallel, right? So that is only possible, right? So here, so if you want to integrate this one, or if you want to integrate these two things, right? So what are the things we need to do is that, so we need to convert this into a practical current source, right? So we need to convert this into practical convert source. So if you connect an inductor, okay, if you connect an inductor, so what will happen? This entire thing will act as a voltage source or a current source? Or practical voltage source. So inverter is there. So in series with that, you are connecting an inductor. So how it will behave? A current source or a practical voltage source or practical current source?
Depending on inductor value, it may act as current source.
So it will acting as a practical voltage source, right? So this entire thing acts as a practical voltage source. Okay. So let us assume that, so where this, for example, this is the instantaneous voltage and this instantaneous voltages are different. So this one, or this inductor acting as a medium, this inductor is acting as a medium to match their instantaneous values, to match their instantaneous values, right? So whatever the remaining voltage drop, so the voltage between this grid minus the voltage of the inverter, so that is appearing as voltage across the inductor. Agree? The remaining voltage or instantaneous voltage difference, so that will appear across the inductor. So that's why, so these inductors are known as coupling inductor. So this is known as coupling inductor. So that means that is used to couple the inverter to the grid. Okay, so that, so this integration can be possible. So here the thing is that, so whatever the difference or instantaneous difference in the voltages of the grid and inverter, so that is appearing as a voltage across the inductor. So that appearing across the inductor. So this is known as coupling inductor or coupling inductor. And this point, so where exactly we are connecting the inverter, so this is known as PCC. Okay? So that means point of common coupling. So this is known as point of common. So anything, not only inverter. If it is inverter is connected to a battery energy storage system, or if it is connected to some solar, or if it is a D-STATCOM or a STATCOM or anything, right? So if it is something is connected to some point, right, that particular point is known as point of common coupling. So but it is done by using an inductor, so that inductor is known as coupling inductor. So let us assume that, so this coupling inductor, so it is either it is external one, so either it is external one, or sometimes for protection point of view, sometimes from protection point of view, so this inverter is connected by using a transformer. So before connecting the inverter to the grid, so we normally use a transformer. So here the transformer serves three things. This transformer serves three things. So one is voltage matching. One is voltage matching. So what is the meaning of voltage matching? Let us assume that this grid is 11 kV. This inverter is 2.3 kV, right? So you require a transformer, so which can step down the, you require some step down transformer here. So 11 by 2.3 kV transformer is required in between, right? So that means it will match the inverter and the grid voltages. So it will match the inverter and the grid voltages. So that is the first thing. So you may not get the required voltage. For example, this voltage is higher than that. For example, it is 132 kV. So constructing a 132 kV, so it is a costly thing. So therefore, so one of the easiest way is to step down. For example, step down to 11 kV. So you can place 11 kV inverter here. So that means it will act as a voltage matching. So that is the first thing. And the second thing is, so it will act as isolation. So whenever some fault is occurring, so this transformer will isolate. For example, if you have a fault on the grid side, okay, so that means if the fault on the grid side, so this transformer acts as an isolation and it will, right, so whatever the fault is there, so that will not propagate it to the inverter side. So it will act as a isolation. And another thing is that, right, so as we already discussed that, so when inverter is there, if you want to connect to a grid, so you require a coupling inductor. Okay, so here the transformer is having some leakage inductance. So normally transformers is having some leakage inductance. So the leakage inductance in this transformer is acting as a coupling, or if this leakage inductance of the transformer will act to couple the, or acting as a coupling inductor. All right. The leakage inductance of the transformer will act as a coupling inductor. So when the inverter is connected to a transformer, the transformer basically serves mainly three things. One is the voltage matching, and it will provide the isolation, and it will serve as a coupling inductor. So the transformer leakage inductance will act as a coupling inductor, right? So depending on that leakage inductance requirement, right? So either you use this leakage inductance of the transformer. So normally transformers are designed to have some minimum leakage inductance, right? Okay. So simply we require some inductance. So that means we will not design the transformer with the required leakage inductance. Okay, let us assume that, so for to couple this inverter, you require some 5 millihenry inductance. Okay, right. So we will not design a transformer with 5 millihenry. Okay, right. So transformer is having, so when you're designing the transformer, we'll try to reduce the leakage inductance as much as possible. Okay. So let us assume that the transformer leakage inductance is 1 millihenry, right? So remaining 4 millihenry, so that is supplied from the external inductor. The remaining 4 millihenry, so that is supplied from the external inductor. So that is how it is done. If this transformer leakage inductance is self-sufficient, so we will not connect any external inductor. If it is not sufficient, so we need to connect. So one of the, or the difference amount we need to connect. Right. So another advantage, so with this coupled inductor is, so it will suppress the high frequency harmonics, or high frequency harmonics in current. So this high frequency harmonics, so this is comes from the PWM operation of the inverter. It comes from the PWM operation of the inverter, and this high frequency harmonics, so these are suppressed by these inductors. Okay. So either, so we'll directly connect this one, or else we can use this LC. We already having some inductor is there, right? So what is the extra thing is, we need to connect some capacitor, so that will act as a low pass filter, or that will act as a filter to reduce the, or to eliminate the harmonics which are arised from the PWM operation. Right? Right. So these are the main things. So what we observed that, so to couple the inverter to the grid, you require a coupling inductor. So generally, so if it is connected to the transformer will act as a coupled inductor. If the transformer leakage inductance is not sufficient, so we need to add some external inductance to the circuit, or we need to add some external inductor to the circuit. Okay. And this point is known as point of common coupling. So where exactly we'll connect the, or where exactly so we'll integrate to the grid. So it may be an inverter, or it may be anything. Right. So other thing, so when you're integrating to the grid, so the one that required is PLL. So what is PLL? So what is PLL?
Phase log loop.
So PLL is known as phase lock loops. So what is the purpose of this phase lock loop? What is the purpose of this phase lock loop? So why you might have studied, right? What is the purpose of this phase lock loop?
Synchronizes the output signal.
Hmm.
Synchronization purpose we use
So for
PLL.
synchronization, right? So you require phase lock loop. So you remember in your BTech level, so you might have done the experiment, so synchronizing the alternate, so with your grid, right? So you remember that. So how you are synchronized by using some lamps, right? So based on the lamp illumination, right? So we can find out the difference voltage. So whenever the lamps are completely off, even though you are giving the power supply, the difference between those two are minimum, so therefore the lamps are not glowing. So at that point, so you are aware that the instantaneous values of those two are matching. Okay, so at that point, so you turn, or at that point you will close the switch so that the alternator is connected to the grid, or alternator is connected to your lab supply, right? In the same way, so these are the phase lock loops. So basically it is used to help to synchronize this voltage source inverter and this voltage source. Okay, so here, so we must know the, for example, whatever this grid is there, right? So grid is operating with some frequency and it is having some phase angle, right? So therefore we must accurately know the value of this omega t and this theta. In other words, if the grid A phase voltage is Vm sine omega t plus theta or some phi, so you must have a data of this omega t and this phi. So that can be obtained so by using these phase lock loops. So by using these phase lock loops. So usually the phase lock loops are something similar to this. So this is usually phase lock loops. So this one, so we have PD, phase disposition or the phase difference. So this is loop filter, and this one is the voltage controlled oscillator. So this is one is voltage controlled oscillator. So here the first thing is, so these voltages are converted into, the voltage are converted into, so what we have to do is, so by using alpha beta to DQ, so that means the voltages are converted into DQ reference frame first. The voltage are converted into DQ reference frame first. So in this VD and VQ, so this VQ having the information of voltage magnitude, right? So here in case of VQ, so you have information on the phase angle. So we'll process this VQ. So VD, so what exactly this one is? What is this? kV by S in plus 1 plus kV. What is the transfer function of this? So what is its transfer function of this? kV by 1 plus skV. So it is a low pass filter, right? So it is a low pass filter. So by using this low pass filter, so we have the information of this magnitude. Similarly, this VQ, so it is processed in a PI controller. So by using this PI controller, right? So we'll have the information of this omega, right? So integrating this omega, so you can get the theta value. So from this theta value, so we have this voltage source controller. So more details, we have one video on this one, so you can observe that. So where I discussed about the different PLLs. It's a single phase PLL and 3-phase PLL. So you can go through this. So more information is not required in this class. Only thing is that the phase lock loops that gives you this theta. Okay. And also it will give you, if you are using a MATLAB, so that gives the information of sine omega t, in other words sine theta and cos theta. So that also gives you magnitude value. So you can And watch that if you require more details about this phase lock loop. So basically phase lock loop gives you the frequency information and the phase angle information, right? So this helps in obtaining the synchronization signal between the synchronization between the grid and the inverter. You're aware that so when you're using ABC to DQ transformation, you must require the value, or you must require the information of this theta, right? The phase angle difference that is required, right? So this theta can be obtained by using the phase lock loops. So now, so when you're integrating to the grid, or when you're controlling this P and Q, you can control P and Q, or if you have inverter, you can control the voltage across this VDC and Q. So VDC and Q. So let us assume that we have some so usually you connect a capacitor, so that will smoothen the ripples. So let us assume this is load. Let us assume we have some R load. So these are the grid. All right. So these are the switches. So this is basically the simple representation of a inverter. So before that, so we have some coupling inductors will present. All right. So let us assume that, so this voltage is VDC. So let us assume that voltage is VDC. So assume that the losses in the switches are 0, or the switches are ideal. Losses in this inductor is 0, and the losses in the switches are 0. Right. So now the question is, if this voltage is VDC, so how much active power so that is injected to the grid? So load resistance is R. So how much active power so that is injected to the grid? So some voltage is injecting, right? So P is injecting here and the Q is injecting. So how much active power so that is injected to the grid in this particular case? If you assume that so switching losses are 0 and the inductor losses are 0. And otherwise, inverter is ideal.
0, P0, P0.
What?
Active power is 0.
Active power is 0. Why it is 0? Why it is 0? You just observe that, so we have this element, right? So whatever the injected power, so this is PAC, which is equal to PDC. Agree? It is the inverter is ideal. So PAC, right? So it is PDC. So what is PDC here? What is PDC? You know the resistance value. So what is the volt? You know the voltage value. What is the formula?
VDC square by R.
So that is VDC square by R, right? So the power is VDC by R. So let us assume, so we'll talk in terms of, we'll quantify this one. So let us assume this is the one, right? So how much it is? 100 kilowatt. So let us assume R is 10. So what is the value of VDC? So what is the value of VDC? How much?
1000.
The VDC is 1000, right? So what we observed that, right? So we'll talk about the reactive power later, right? So what we observed that, so if this voltage is maintained, so 1000 volts, right? So the power, so that gives you is, so how much it is? 100 kilowatt. All right. So 100 kilowatt. So that means, so we can either fix this P value, or in other words, we can control P, or we can control VDC. Either we can control P or we can control VDC, but you cannot control both, right? If the load is constant, so we cannot control both. Similarly, so let us assume that, so this is voltage is VDC. In the same case, the same manner, so let us assume that P is having some value. For example, 4. So this is 400 kilowatt. If P is 400 kilowatt, if R equal to 10, right? So in the same parameters, so can we fix VDC value equal to 1000? Can we fix like this? Can we fix this? So it is not possible, right? So what is the exact value? If this P is our, if active power we are controlling, right? So what is the value of this VDC? So what is the value of this VDC?
2000.
It's 2000, right? Okay. So there are two options. So either, so we can fix the value of VDC, or we can regulate the VDC, or we can regulate the active power. Only one thing is possible. So let us assume that, so you're fixing this value, some VDC, for example, you are fixed as 900 volts. So in that case, so you cannot control the active power. So now active power will by default, it will become, so 900 square by 10, somewhere around 81 kilowatt. So that is your active power. Okay. And the thing is that, so this is about, so either you can control the P or you can control the voltage across the DC side, right? So here there are numerous applications, right? So for example, so when you will control the voltage across this DC side, if you have a operating as a motor drive, so in that case, so you have alternatively, you have on the other side, you have an inverter is placed, right? So AC is converted to DC and DC is converted back to AC. So now this entire thing acts as a front-end converter. So that is useful for a motor drive application. Or you have some applications, so this this resistance we can replace with a battery energy storage system. So we can replace with a battery energy storage system. So batteries can be charged in multiple ways, right? So either we can keep the voltage constant, or you can keep the current constant, or we can keep the power constant. Batteries can be charged by using multiple ways. So voltage constant, current constant, and the power that is constant. So in that case, both voltage and current will be varied. So either voltage will be fixed again, or current will be varied, or the current will be fixed and the voltage will be varied. So now the batteries can be charged multiple ways. You can keep the voltage constant, and the power, you can keep the current constant, or you can keep the voltage constant, power constant. So when you are keeping the power constant, we have multiple options. We can keep the voltage fixed and the current variable, or the current fixed and the voltage variable, and still the power is constant. Right. So in this approaches, so we can keep this VDC constant. Yeah. So in case if you are integrating that, so let us assume that we have some PV panel is there. So in that case, we need to control the active power. In that case, you need to control the active power. All right. So application, so either we are controlling the active power or voltage across this DC side. So that depends on the application level. All right. But the thing is that, so only one thing is possible. So come to the reactive power. So in this case, not mostly, so we'll keep this reactive power is 0. Agree? In most cases, so we'll keep the reactive power 0, right? If the reactive power 0, so in that case, and if the currents are controlled to operate in unity power factor or sinusoidal, so in that case, the inverter it will operate at unity power factor. So inverter is operating at unity power factor. So most of the cases, so if we will operate, so Q as 0. If it is a motor drive, so in most of the cases we'll operate Q as 0. If it is a charging application, battery energy storage system, so we'll keep Q as 0. So when we will control Q, so when we will control Q, so when we will control Q.
For voltage stabilization. For voltage.
Voltage?
For improving voltage.
So let us assume that we have some applications. If you want to have grid stability, so if you talk about the grid, right? So when you exactly will control this Q, so let us assume some fault is happening, right? So with the fault, the voltage will be fluctuating, right? So voltage is fluctuating. So if you want a fluctuating voltage, okay, so that means, so by injecting some equal and opposite reactive power, so we can regulate the voltage. Agree? We can regulate the voltage. So during the fault cases, so most of the times, so we need to generate or we need to control the reactive power. So that means whatever the reactive power that is present, so during the fault, that we can compensate that. So in that case, we can use that. So let us assume another one. If it is an induction generator, so let us assume that we are integrating an induction generator. So that is wind energy. If it is a wind energy, so you're aware that, so for wind energy, you require a lot of reactive power, right? So that's why, so we normally connect a capacitor banks across the induction generator, right? So earlier days, so we normally use these capacitor banks. So these capacitor banks requires a lot of maintenance, and so moreover, the control of the reactive power is not accurate. So therefore, so here inherently, when it is connected to the grid, right? So that means whatever the reactive power that required for the induction generator, so that is provided from this control of Q. The control of Q. Okay. Similarly, if you have voltage, for example, in case of microgrid, so microgrid, so the fluctuations of this frequency and the fluctuations of this voltage are common, right? So if you have fluctuations in frequency, so how you will control that? So let us assume that fluctuations in frequency. So how you will control that? If it is fluctuations in voltage, so that is controlled by Q reactive power, right? If it is a fluctuations in frequency, so how exactly you'll control? Thing is that, so when you control the active power, the frequency fluctuations can be reduced. Okay, right? And if we have voltage fluctuations by controlling the reactive power, so we have, or we can control the, what we say, we can control the voltage fluctuations by controlling the reactive power. So that's why most of the micro grid applications, we have something called battery energy storage systems will present. battery energy storage systems will present. Right. So what is the objective of these things are? So whenever there is a fluctuations in the grid, so energy stored in the battery, so that is given to the grid. So some fluctuations in the battery. So that means voltage, if you observe that frequency fluctuations are there, some active power is injected to the grid, or excess active power that is generated from the grid, so that is injected to the battery energy storage system. So that's why, or so that the frequency fluctuations can be minimized. Similarly, if you have reactive power fluctuation, or if you have voltage fluctuations, so it's the same battery energy storage system, so that is operating as a STATCOM mode, right? That is operating as a STATCOM mode, so that is regulating the voltage across a particular bus by injecting the required amount of reactive power. So that's why, so this active and reactive power control is compulsory, especially in transmission applications or in case of microgrid applications. So this is mostly achieved by using a battery energy storage system, or sometimes we use UPS. So large UPS, UPS and battery energy systems are more or less same. That is UPS, so that is a line controlled UPS. We normally use line controlled UPS to achieve this task. So that's why in every microgrid applications, you will found 1 or 2 battery energy storage systems. The objective is to control the active and reactive power so that the grid frequency can be stabilized and the voltage can be stabilized. All right. Right. So these are the reasons. So why exactly we need to control the P and Q. So now the thing is, so how to control this one? So that, so when you're controlling the active power, the reactive power must be uncontrolled or must be independent, or in other words, independent control of active power and reactive power. So how to achieve independent control of active and reactive power? So that is known as decoupled control. So that is known as decoupled control. In other words, decoupled current control. So if you understand what is exactly the decoupling means, so you must go back to DC machines. Right. So there are two equations. So that is back EMF. So what if it is assume that is a motor? So what is the formula for back EMF? P phi N Z by 60A, right? Agree? Right. So we have a relation. So from this, what is the relation can be obtained between the flux and N? So what is the relation so that can be obtained from this flux and N? So will it be like this? N is proportional to 1 by 5. Agree? If you assume that the back EMF is constant, the number of poles are constant, conductors are constant, and this is A, the number of parallel paths are constant. So once the machine is established, so this N is proportional to 1 by 5, right? So this phi is related to what current? Field current or armature current?
Field current.
So field current, right? So that means N is proportional to 1 by field current IF. Okay. So let us assume that it is a shunt machine or a separately excited machine. In case of shunt machine, the field is usually constant. So we assume that it is usually constant. Obviously for separately excited machine, so it is always constant. Right. So for shunt machine, we assume that the field is constant. In case of separately excited machine, so that is by default, the field is excited with separate supply. So therefore that is constant. So that relation is N equal to 1 pi. So there is another one. So what is the relation for the torque? What is the formula for torque?
Current.
What is the formula for torque? You're aware of that?
Pi into IA.
It will be something like this, right? 0.15 0.159 Z phi IA by P by A. You remember this? This is the torque equation for a machine. Okay, so where this Z is the number of conductors, so phi is the flux per pole, and this IA is the armature current, so P is the number of poles, and A is the number of parallel paths. So from this, TA is proportional to this phi into IA. Remember this, I think. So if we assume that the flux is constant, so that means the torque is proportional to armature current IA. The armature torque is proportional to armature current. Right. So this is under the assumption that the flux is constant. Right. If it is series machine, the flux is proportional to armature current is also. So that's why the torque is proportional to Ia square. So that's why the series machine having the highest or the theoretically infinite torque. Right. So that's not our discussion. So let us assume that what we observed that, so in case of generally, so when you're controlling any motor, so either we'll control the speed of the motor or the torque of the motor. In the same way, right? So in case of induction machine, in case of DC machines, you have two currents. So one is IA and IF. So this IA is responsible to control the torque. So whereas this IF is responsible to control the speed. Right. So if we assume that this is separately excited machine, right? So in that case, so when you're controlling this torque, or in other words, the torque control is independent of speed control, and the speed control is independent of torque control. Okay. So that's why these DC machines are popular. So in early days, these DC machines are popular. So because the speed control is decoupled. So torque control and the flux control, so both are decoupled. All right. So later, the thing is that, so once there are disadvantages with DC machines, you're aware of this, right? So later, so induction machines are invented. So even though it is invented, right? So here this decoupling is not possible in early days. So we have no separate control for, there is no separate control for the torque and separate control for the flux. So later, so once this scalar control, or once this reference frame theory is invented, or once we applied the reference frame theory to this induction motor, so there we can control the separate for, so ID, so we can control, or we have this three-phase currents in the three-phase stator currents, so that we can convert into two-phase by using this ID and IQ. Right. So by using this ID and IQ, so we can separately control the speed and we can separately control the torque of the machine. Right. So now, so once this is invented, so nowadays these induction machines are popular now. So that is the main reason. So why these induction machines are popular. So early days, so we cannot control, we have no separate control of torque and speed. So but by using this three-phase to two-phase transformation by using this DQ reference frame, so we have separate control of torque. So that means ID is responsible for torque, or right, and IQ is responsible for speed. So therefore, so we have decoupled control of induction machine is possible, right? So this is basically, this is obtained by the direct torque control or the vector control. So by using these two techniques, so we can control the torque, the starting torque of the machine we can control, the steady state torque can be controlled, or we can seamlessly control the speed of the machine. So this is basic idea of, so how exactly the decoupled control originated. Right. So now in the same terms, so when you're using the same theory for inverters, So we have three-phase inverter, voltages are there, and three-phase inverter, currents are there. The first step is, so we need to convert this into DQ0 reference frame. So we need to convert this into DQ0 reference frame. Okay. So that means the variable one, so will become a DQ0. So that means this will be the VD, right? So if the magnitudes are balanced supply, so the what is the value of VQ? So what is the value of VQ? What is the value of VQ? If the initial conditions are 0, so what is the value of VQ? In case of balanced supply. Hmm? No idea. VQ is 0, right? I think you have experiment on this also in lab. Power invariance of, you have some experiment is there, right? What is that? Power invariance in different reference frames. So this VQ value will be 0. So we'll come back to this. So we have these voltages are there and currents are there. So let us assume that, so that is calculated by using power invariance. So power invariance is used. Right. So in case of power invariant, so in that case we need to use K equal to root 2 by 3, right? So remember when you're studying the space vector modulation, so we used as 2 by 3. Okay. So why you used as 2 by 3? Because we are dealing with the voltage magnitude. So that means we require the voltage invariant expressions. So that's why we use 2 by 3. So now we are talking about the powers. So therefore we make sure that so the equations in a power invariant form. So therefore we are using the term root 2 by 3. So what is the active power? P. What is the expression for active power? P. So you remember this. So VD ID plus VQ IQ plus V0 I0. So usually this term is 0 for balanced. And the cover and Q. So what is the value of Q? So this is VD IQ minus VQ ID minus VD IQ. Right. So you're aware of these two terms, right? So one is the active power, so VDID, VQIQ plus V0 I0. And Q is VQID minus of VD into IQ. Right. In case of balanced supply, right, and A phase is synchronized with D axis. So if A phase is synchronized with D axis, so in that case only VD value will exist and this VQ value will be 0. Right. So that means if the initial conditions both are matching, so both are rotating at the same speed, right, and it is synchronized, and the A phase and the D axis are synchronized, so in that case the VQ magnitude will be 0. So now if the equations can be simplified, so it will be VD into ID and Q will be VQ into ID. This term is 0 and these terms are 0. So your P is VD into ID and Q is VQ into ID. Understood? So these are the original expressions. And this is, so how we simplified, so VD into ID. So from this, so this is minus VD into IQ. Okay. So this is all depends on the current direction. This is change here. So this will be VD into ID minus PQ into ID. So earlier one is from the power flow. So depending on the power flow. So here the power is injecting to the grid, or that means depending on the direction of, so let us assume that this is the one and we have this inverter. This is the power flow, or so this is the power flow, right? So based on that, so these equations will usually change. So that one, so we are using this. So this is based on this. The power flow is from source to the, so the grid to the inverter. Okay. So if it is this one, so Q will be, so V, just reverse of this, VQ into ID minus of VD into IQ. Understood? So both are same, just thing is that, so we need to use the negative symbol, that's all. So this is power is flowing from, so grid to the inverter. All right. So that's why it is VD into ID. So therefore this will be VD into IQ. So Q is VD into IQ. All right. So from this, so this ID value can be obtained. So how to obtain this ID? So P by VD. So that gives you ID value. And this IQ value is Q by VD. That gives you IQ value. So keep this aside. So come to here. So this is basically, so how you will connect the inverter to a grid. So you have this utility grid is there here. And the other side, so you have this inverter. Right. So voltage source converter. So this is VTABC. So that is the terminal voltages of the inverter and the current of this inverter. And this is the grid voltages. So VABC. And we are using a coupling transformer here, right, along with that. And this is the PCC, point of common coupling, right. So these are the inverter coupling parameters. So by considering all the parameters, we are lumped together this LT into RT. RT is the coupling resistance, right? Usually this value is very small, and this LT is the coupling inductor size. So when you are measuring this LT and RT, so we are also included this grid side parameters also, right? Grid side inductance and this coupling transformers. So everything we are lumped together here, right? So we'll discuss this in the next class. So have any questions? Have any questions? So if you have no questions, we'll stop here.